So we talked about the Butler-Volmer equation, and we said Tafel equation is a simplification for Butler-Volmer equation when there is large either positive overpotential or very large negative overpotential. Okay, so let's check the deviation of Tafel result from Butler-Volmer equation. Still assuming no transport limitation. Still assume no transport limitation. The concentration of different species are all the same in the system. And then let's plug some numbers. Assume J0 exchange current density 0.05 amp per square centimeter. Symmetry factor beta still 0.5. Temperature still 25 degrees C or 298.15 Kelvin. And the number of electron transferred is still 1. So with these um, numbers, we can plot the Butler-Volmer equation as well as from Tafel equation. Here, the black solid line will be the current over potential plotted based on Butler-Volmer equation. Here, the horizontal axis would be natural log of current density. The vertical axis would be over potential, and then using the Butler-Volmer equation for each of the over potential, we can calculate the uh, current density, and then we only look at the positive or anodic overpotential, and the current would be positive, and then we plot eta versus natural log of current density. Of course, here we put natural log of current density as horizontal axis, eta over potential as vertical axis. So that Butler-Volmer equation gives us this solid black line. On the other hand, this blue circle line is from the Tafel relationship. We said it's an approximation, okay? When the overpotential A value is very large, let's only look at the anodic overpotential, or when the overpotential is positive, and then this would be the relationship in exponential term. And if we can, of course, rearrange this into the typical linear function between overpotential and the natural log of current density. Eta would be vertical axis, natural log of current density would be horizontal axis. And then if we have this relationship, we would have a strictly linear relationship with the slope term b equals to this one RT over 1 minus beta times NF. That gives us the slope for this Tafel relationship between overpotential and the natural log of current density. And the intercept, this is the intercept, the y-intercept or the eta overpotential intercept, which is this value, would be given here. Okay, this is the intercept for y-intercept or eta-intercept. On the other hand, we can also have this line extended all the way to eta equals 0. So if eta equals 0, we would have the natural log j intercept, and that would give us the natural log for the exchange current density. For natural log of exchange current density. So if natural log of J equals to natural log of exchange current density, then eta would of course be 0. Okay, so these are the special points on this plot. Then we are talking about deviation from Tafel, from this blue versus from the precise calculated Butler-Volmer. As you can see clearly, when the over potential is low, is close to zero, the relative error would be large. For example, even at over potential of 60 millivolts, slightly higher than here, then the current and density calculated from Butler-Volmer equation is 0.145 amp, while that calculated from Tafel relationship is only 0.161 amp per square centimeter, and the relative error would be 11%. On the other hand, if we increase the over potential to 100 millivolt, or 0.10 positive volt, then the current density calculated from Butler-Volmer would be 0.343 amp per square centimeter, while the one calculated by Tafel relationship would be 0.350 amp per square centimeter, and then the error in this case would be 2%. The error in this case would be 2%. And of course, with even higher over potential, the error would be even less. So this again illustrates there will be deviation for Tafel relationship, which is approximation from the more precise Butler-Volmer equation. And the error is very large when the over potential absolute value is small, but it's getting negligible once the over potential is 100 millivolt or higher.